In chapter 1.2, we will introduce four basic quantities, which are current, voltage, power, and energy. First of all, we will introduce what is electric circuit. The definition is that an electric circuit is an interconnection of electrical elements. The definition of electrical elements will be discussed in chapter 1.3. But let's take a look at two examples. On the first figure, we have a battery, a lamp, and the battery is supplying power to the lamp. And it can be represented by mathematical models as shown in this figure. We can represent the battery, and we also use resistance to represent the lamp, and we have the solid line to represent the wire. So we build the circuit. So the second example is a vehicle. It has wires, battery, switch, and headlamps. It has two headlamps. So similar to the first example, we have the model for the voltage source, that is the power supply. We also have the model for the switch, and we use two resistors in parallel to represent the headlamps. So the electric circuit is an interconnection of electrical elements. The elements here can be the resistor, or it can be the power supply, the voltage source. In the previous slide, we introduced two very simple circuits. Of course, the circuits can be more complicated. It can consist of multiple elements. You can see in this figure we have multiple resistors, and we also have the capacitors and the inductors. We will introduce the capacitor and the inductor in chapter 6. For the complicated circuit, we usually conduct the analysis not by hand but by some software. In this course, we will introduce the PSpice, which is the software widely used for circuit analysis. And by the way, the goal of circuit analysis, what is the goal of circuit analysis? It is to obtain or calculate the voltage and current on each node, on each component, on each element. We will discuss the node and the loop in chapter 3. As I introduced that, we will introduce four quantities in this lecture, and these four quantities are widely used in our daily life. For example, this is the charger for my iPad. We can see on the label it has 10 watt. The 10 watt is the unit for the power. We will introduce it later. And also the input is 100 to 250 volts. Volts is the unit for voltage. And the 0.45 ampere, this is the unit for current. And 50 to 60 hertz, this is the frequency of AC voltage. We will talk about this later. And the output is 5.1 volts, that's the output voltage, and 2.1 ampere, that's the output current. And this symbol, it represents the DC, and this symbol represents AC. We will talk this in detail in the following lecture. For the current, we learned current in our physics course. The definition of the current is the time rate of change of charge. So it is the rate of change of charge. So IT equals dqt over dt, depends on how fast the charge changes. And 1 ampere equals 1 coulomb per second. Let's take a look at an example. If the current in an electric conductor is 2.4 ampere, how many coulombs of charge pass any point in a 30-second interval? We have the definition I equals dq over dt. And we know that I equals 2.4 ampere. So that the changing rate of charge is a constant. The changing rate is a constant. And we know that the delta t equals 30 seconds. So what is delta q? Of course, it equals the changing rate multiply the time, 30. It equals 22 coulomb. The other example is that the charge is known. If 60 C of charge passes through an electric conductor at a constant rate, this is very important, in 30 seconds, determine the current in the inductor. The current equals dq dt, and we know the delta q and the delta t. The delta q is 60 and the time is 30 seconds, so it equals 2 coulombs per second, that is 2 ampere. And the definition of the direction of the current, even though the current flow results from the electron motion, the universal convention, so this is our convention, is that the direction of current represents the movement of the positive charge. For example, in this we can see the electron moves in this direction. However, the current, the direct direction of the current is shown in the second figure. It flows in this direction. We will talk about the direction later, because when we talk about the current, we not only talk about its magnitude, but also its direction. Here, let's take a look. This figure A shows an example. From the circuit, the current equals 2 ampere. And we have this arrow represents its direction. It is from left to right. So the actual current is from left to right, and the magnitude is 2 ampere. The second figure, figure B, the arrow of the direction is also from left to right. However, the current is a negative value. This negative sign means that the actual current, the direction of the actual current is opposite direction of the reference current. So the actual current is 3 ampere from right to left. So it indicates the 3 coulomb of charge passes from right to left. So as I talk about that, the current has magnitude and the direction. So it is shown in a circuit diagram by an arrow. And we can see that these two are the same. We have the reference direction from left to right. and 2.6 ampere. So the actual current is from left to right. And the second figure, the arrow is in the opposite direction, but the current is a negative value. We can move the reference direction. The original reference direction is from right to left. We can reverse the reference direction from left to right, and we need to remove the negative sign. So this is 2.6 ampere from left to right. So even though the reference direction is different, but the actual current is the same, that is from left to right. So let's another example we assume is A to B. We know that there's 5 ampere current flowing from point A to point B, right? And we can also say that the current from B to A is negative 5 ampere. They are equal, they are equivalent. But we can select another reference direction, not from B to A. Here we select the reference direction from A to B and remove the negative sign. So this becomes 5 ampere. So these two are equivalent. So let's take a look at what direction is the current flowing, the actual direction. We can see that the reference direction is from up to down and the current is positive. So the actual current is from up to down. And the second one is that the reference direction is from down to up, but it's a negative. We can make it a positive one. So we reverse the reference direction and I equals 2 ampere. So the actual current is flowing down. The third one, the reference direction is up and the current is positive. So the actual current is up. And the last one, the reference direction is from up to down, but the current is a negative value. We reverse the reference direction and the I equals 6 ampere. So the actual current is from down to up, go up. So the current values are defined with a magnitude and a direction. So when we talk about the current, we not only talk about its magnitude, we also talk about its direction. And in the previous slides, we used the arrow to represent the direction, the reference direction. And the reference direction can also be indicated by labeling the ends of the circuit elements using the double script on the current variables. For example, here we have current IAB, which means that the reference direction is from A to B. And if we have IBA, this means the reference direction is from point B to point A. And they are reversed. IA equals the negative IAB. So both IAB and IBA represents the same magnitude of current, but in opposite direction. Then let's talk about the AC and the DC. In the iPhone charger, or not iPhone, iPad charger example, the label, the input is AC, the output is DC. AC is the current that it can be current or it can also be the voltage. We have the AC voltage and the AC current. Is that for the DC it remains constant with time, and AC is that varies sinusoidally with time, and the frequency of this sine wave for some countries is 50 Hz and some countries is 60 Hz, And for the charger, it works, the working condition is between 50 to 60 hertz, so it works well in this frequency range. And in the multimeter, we have this one. We will use this one in our lab course. We can see that the label of DC current is like this, and we also have the label for the AC current. It looks like this. So you need to make sure, you need to know the current you are going to measure is DC or AC before you select which one to use. And for the voltage, when we talk about voltage, we usually talk about the voltage between 2 points. And it is the difference in energy level of a unit charge located at each of the 2 points. So we have the definition of the voltage. Let's take a look. So here we have the X and Y. These are 2 points. And we have a unit charge. We move the unit charge from position X to position Y. And the energy we use to move this unit charge from point X to point Y is 1 joule. So the voltage between point X and point Y is 1 volt. So the 1 volt equals 1 joule per coulomb. So the voltage is a relative potential and has magnitude and direction, the same as current. It is shown in a circuit diagram by usually a plus or minus sign labeled with a magnitude, as shown in this figure. So this can be understood as the voltage at the positive point with respect to the negative point. So let's call it point A and point B. So we can also write VAB equals 10.3 volts. So in the circuit with a lot of elements, instead of using the plus and the minus sign, the points are labeled with letters and the voltages are then described with subscript. So here we have A and B. VAB equals 2.6 volts. And be careful, VAB equals 6.2 volts. What is VBA? It should be negative 6.2 volts, right? So VXY equals VX minus VY, and VYX equals VY minus VX. Let's take a look at the voltage representation. Here we have the V1. The VA here is always the relative voltage from the positive terminal to the negative terminal, so that V1 equals 2 volts, which means that the voltage at point A is 2 volts higher than the voltage at point B. But here the V2 equals negative 5 volts. This means that the voltage at point A is 5 volts lower than the voltage at point B. So VAB equals negative 5 volts. So this means that VA is smaller than VB. The third example, we can see that this is the the plus sign is on B, not on A. So we have VB minus VA equals 5 volts. So the voltage at point B is higher than the voltage at point A. For the voltage and current measurement, we will do the measurements in our labs. Be careful that when you measure the voltage, the connection of the multimeter is in parallel with the resistor. And to measure the current, the multimeter is in series with the resistor. Yeah, we will talk about this in our lab course. And then it's power and energy. They are different. Power is the time rate of expending or absorbing energy measured in watts. Is the rate. It is a rate. So it can be calculated by V times I. Let's take a look at the, before we calculate the power, we need to discuss the passive sign convention, because the different reference direction, the result, even though P equals V times I, right? But with different reference direction, the V and I can be either positive or negative. So we need to have a convention to make sure that they are the same. So here we introduce the passive sign convention. So that is to calculate the absorbed power. So the power absorbed by the circuit element with terminal A and B is equal to the voltage drop from A to B multiplied by the current through the element from A to B. So this is the passive sign convention, that is P equals VAB times IAB, not there are other conventions. For example, VAB times IBA. This is another convention. We will talk about this later. So here remember that the passive sign convention requires that the reference direction is from A to B for both voltage and current. So in this convention, if P is greater than 0, then the element is absorbing power. If the P is smaller than 0, it is absorbing negative power. Absorbing negative power means it is actually generating the power. Okay, now let's take a look at an example. Calculate the power absorbed by the element. We can see that for figure A, it matches the negative sign convention. And so the power absorbed by the element equals 3 times 4 equals 12 watts. And for figure B, it also matches the passive sign convention. So the power is 4 times 3 equals 12 watts. Let's take a look at another example. The second example in figure A, we can see that it does not match the passive sign convention, because the current, if it matches the passive sign convention, the reference direction should be this, right? But here the reference direction is opposite. So what we can do is that we reverse the direction of the current. From here, the direction is from right to left. We make it left to right. And the 3 ampere becomes negative 3 ampere. So the power absorbed by the element equals 4 times negative 3 equals negative 12 watts. It's a negative one, so the element is not absorbing power, it is supplying power. And let's take a look at the example on figure B. Also, it does not match the passive sign convention. So in order to match the convention, the passive sign convention, let's reverse the direction of the current. So the current is negative 3 ampere, so it matches the passive sign convention. So the power equals 4 times negative 3. It is also a negative value. It means the element is supplying power. Supplying. So there are some exercises for you. Calculate the power absorbed by the element in these two figures. And I will give you 1 minute to write down the answer, and then I will discuss the solution. Okay, time's up. Let's take a look. So the voltage, the positive sign is down and the negative sign is up. Of course, it does not match the passive sign convention, so we reverse the current. Alright, so the power equals negative 4 times 2 equals negative 8 watt. So it is supplying power. The element is supplying power. The second one, it matches the negative sign, the passive sign convention. So the P equals negative 2 times 2 equals negative 4 watts. So it is also supplying power. So in the previous examples, we know P equals voltage multiply current. And in the previous examples, we know the voltage and the current. We calculate the power. And in this example, the power is given, and either voltage or current is given, and the other is unknown. You need to calculate. Let's take a look. For example, here we know we need to calculate V, right? And of course, it does not match the passive sign convention, because if the passive sign convention, the current is flowing counterclockwise, but here it is clockwise. So we reverse the direction, and I becomes negative. And we know P is 40. What is V? V equals P over I equals 40 over negative 2 equals negative 20 volts. This means that, let's see, this is point A, this is point B. V1 equals negative 20. It means that B is lower than the voltage at point B is lower than the voltage at point A by 20 volts. Let's take a look at the next example on figure B. On figure B, the voltage is given, the power is given. You need to calculate the current. So here, the 10 volts, it satisfies the passive sign convention. So the I equals P over V equals the negative 50 over 10. It equals negative 5 ampere. This means that the actual current is in the opposite direction with respect to the reference direction. So the reference direction is from up to here, right? But the actual condition is from the bottom to the top. right? This is the actual direction of the current. And Telegon's theorem. Telegon's theorem told us that in an electrical circuit, the total power absorbed is equal to the total power delivered. This is the conservation of energy. So with A, B, C, D, E, F, there are 1, 2, 3, 4, 5, 6 elements. 6 elements. And to conserve the energy, we take the algebraic sum and it should equal to 0. So here is negative 40 plus 10 plus 10 plus 10 plus 5 plus, let's assume this is x, plus x equals 0. So here is 10, 20, 30. 30 minus 40 equals plus x equals 0. So this becomes negative 5. So x equals 5. So the element F, how many watts? Is 5 watt for the element F. Okay, next, this picture shows the newest Model 3 of Tesla. We can see that the maximum charging rate is 250 kilowatt. So here you need to remember that power is a rate. It is a rate. The higher power, it charges faster, right? It's like iPad. For the old iPhone, the the charger is 5 watts, so it charges very slow. And the newest one, the new iPhone, they can support the fast charging, right? They increase the current is also 5 volts, but they increase the current, so the power increases, so it charges faster, much faster. The next one is energy. We just finished talk about the power. Next, let's take a look at the energy. Energy absorbed or supplied by an element from T0 to T is defined in this integration. So the relationship between power and energy is this integration. So if let's give an example. For example, an equipment, the power rating is very large. It has a very large power rating, but it only uses maybe 10 minutes per day. There's another equipment that the power rating is lower than the first one, but it runs 24 hours per day. So which equipment uses more energy? So it might be the second one, right? Even though the power rating of the second one is lower, but the time it operates is longer, so it uses more energy. And also our electricity bill, we not only consider the power, but also take the integration. For example, you have an air conditioner, the same power rating, we have the same. I use it 24 hours a day, but you only use 2 hours per day. Of course, I will use more energy than you, so this can be reflected in my electricity bill. So in electricity bill, the unit, they do not use joule. The energy, they use J, right, joule. But in our electricity bill, it is more straightforward to use another unit called kilowatt hour or watt hour, kilowatt hour. So it is the power multiply the time, kilowatt hour. You pay your electricity bill, so based on how much energy you use. Yeah, this is my electricity bill. LES, I live in Lincoln. So the electricity power utility companies measure energy in kilowatt hours. And there's an advertisement from the website of Home Depot, and this is for the LED light bulb. We know LED is more energy efficient the than other types of than the old one, than the old light bulbs, right? So here it says that the energy used is 9 watt, equivalent to 60 watt incandescent light bulb. Is this correct? Yeah, of course it's not correct. You cannot say that the energy used because let's see, this is a power, not energy. 9 watt is power, not energy. Energy you need to take time into consideration. Time. For example, even though I have the LED, I use it maybe 10 minutes per day. Oh no, I use 24 hours per day for LED. But for the incandescent light bulb, I use 1 minute per day. So which uses more energy? I think it should be. I didn't do the calculation, but without time, we cannot talk about energy. Energy not only considers power, but also considers time, the operation time. Okay, that's the end of this lecture. Yeah, thank you.